right, good morning, everybody. Welcome on in, discussing probability and understanding. We're continuing our discussion with probability, understanding that the ability to do probability well is it's important in your everyday life. So getting a little bit good at probability can just help you in general, right? It's like being able to read better, right? You're going to get a little more stuff. Oops. Looks like I have a setting I need to fix here. There we go. Okay. And it's definitely important to understanding statistics. What's going to happen is we're going to start getting into things where probability is part of the system. When we get into hypothesis tests, which you don't know what that is yet, but the end of the hypothesis test returns what we call a p-value. That p-value is literally a probability. That's what the p in p-value stands for, is a probability. It's telling you this is the probability that this event occurred under the conditions that you have laid out. Okay, so understanding how that probability works is kind of important to being able to interpret a hypothesis test correctly. I definitely get students that memorize how to do a hypothesis test, and they just memorize, when I get certain p-values, here's what I do, but they don't understand what they're doing. What's the point of taking a class like this if you're going to get through it and have no concept of what you're doing, right? And some students have that mindset of, well, I'll just get my C. If I can just pull off a C in probability or in statistics, then we'll be fine. But likely there's a reason that whatever degree you're pursuing has told you to go learn some statistics, because you will at least occasionally need it in the job that you're doing. And if you don't know, right? I mean, here's one thing that you see all the time in the job market. You'll have a group of people, and maybe 80% of them didn't really learn the math they were supposed to learn, and 20% of them did. Guess who are the ones that are going to move up through the system, right? It's the ones who usually can do the mathematics and do the problem solving that's necessary to get things done. So really understanding to have that actual fundamental understanding of probability, okay? So we're getting into a new part, the addition rule. So let's check out what that's about. What's the addition rule? So we've talked about the basics of probability. That is, we've done some definitional problems where the problem is just very direct, right? When you want to calculate a probability, you've got your fraction. The numerator is the number of times that the thing that you're counting occurs. The denominator is the number of ways that anything can occur, basically, right? So you know, depending on the type of probability problem you're doing, you know, the denominator is the size of your sample space. The numerator is the number of ways that your event can occur. That's like just the direct application of probability. Well, a lot of probabilities get more complicated than that. They get a little bit harder to calculate. They're just more complicated, right? So we can say, okay, here's a bag. There's 3 different colored marbles in here. Here's the number of each color marble. What's the probability that you pull out a green marble? Okay. Well, what if we start getting into more complicated stuff, like what is the probability of pulling out a green marble or a red marble? Right now it's a little more complicated. Now, some problems like that, you can still actually calculate directly, right? But some are going to be a little more complicated. What if you know, you have 2 unrelated events? You're going to have to use more complex tools in order to calculate those probabilities. So here's what we're getting into. We have a thing called a compound event. So here's our definition. A compound event is any event combining 2 or more simple events. So let's say you have a dice in front of you and you have a coin in front of you, right? So you could figure out, well, what's the probability that I roll a 2 or a 3 on this dice? Well, that's going to be 1/3, right? Because there's 2 ways to get those results. Out of 6 possibilities, 1/3. But what if you said, what is the probability that I roll this dice and I get a 4 or a 5, or I flip this coin and get a tails? So you do both. You flip the coin, you roll the dice, They land on the table. What is the probability that I got a tails or a 4 or 5 on the dice? All of a sudden, these events are separate, so we can't just calculate them using one. I mean, I guess you could, but we're getting into, one of the problems with probability is that your sample spaces can get very large very fast, and it gets difficult. And one of the things we'll see throughout the chapter is we get into counting techniques that are more advanced than what you're used to, right? Most of you can do your basic counting that you started doing when you were whatever, 4 or 3, or whenever you started counting, you're counting on your fingers. 1, 2, 3, 4, 5, 6, 7, 8, right? You're using your hands to do that kind of iterative counting. Well, sometimes the problems we do are too large to count by hand, right? What if your sample space is 10,000 long? Are you going to list all that out on a piece of paper? No. So we're going to develop ways of counting things. And even the reason I'm talking about this now, the example I'm giving of flipping a coin and rolling a dice, those events, let's see, what would you have? I guess that wouldn't be too bad. You'd still only have, 12 outcomes? That's not too bad. But, you could imagine we could get this to grow pretty quickly. What if I flipped 3 coins and 4 dice? Now, all of a sudden, you're talking about like hundreds, probably even thousands of possible outcomes. You're not going to list them all the way we were doing when we were doing the very basic problems. So we have to start figuring out how to combine things with an or an and. Okay, so when I say, okay, what's the probability that I flip this coin and get a tails, or the dice comes up a 4 or 5 when I do that, right? And it's slightly more complicated than you might think. Like, it seems at first like it's going to be real easy, but then we go, oh, there's this one thing you got to look out for. This one thing you have to be careful about. So let's see, where is our example? And then we're going to go up and look at this example up here. So our formal addition rule says if we have 2 events, right, the probability of event A or event B. So what's the probability that I roll this dice and I get a 4 or a 5? So the probability of getting a 4 or 5 is the probability of getting a 4 plus the probability of getting a 5 minus the probability of getting a 4 and a 5. Now, if you roll 1 dice, you can't get a 4 and a 5, right? So what's this piece about? This is the part of the problem people forget. What they immediately do is just add together probabilities. But sometimes what you're going to find is when you add together probabilities, you all of a sudden get a number bigger than 1. Probability can't be bigger than 1. How does that occur? Because you're double counting, right? For instance, let's do a problem. Let me do something here. Let me show you what I'm talking about. So, delete this stuff. Okay, so let's look at the probability or. So we have an or going on, okay? So I'm going to show you how to calculate. We're going to do a simple problem so we can calculate it 2 ways because we're going to figure out that something's wrong. So let's take the probability of, we're going to roll 1 dice, rolling a dice. Oh, that's too big. Let's do this on a different page. Probability of rolling a dice and getting an even or an odd. Not an even or an odd. An even. No, I want to do a prime. That's the one I wanted to do. So see how we have the or in there? Let's see. Okay, so, and I can move this a little, give us a little more room. So what's the probability of me rolling a dice and the number that comes up is either prime or odd? Okay, well, let's do it the way that is sort of intuitive for people, which is this is the wrong way of doing it. So I'm going to let you know this is wrong, but it's the way people try to do it a lot. So you would count, okay, well, we already know that our sample space for a dice, that we're using a typical 6-sided dice, the sample space is 6. You can get a 1, a 2, a 3, a 4, a 5, or a 6, right? So the sample space is size 6, but how many ways can I get a prime or an odd? Well, let's calculate this. So the number of ways that I can get a prime number, or the probability of getting a prime number, so out of 6, how many ways can I get a prime number? Let's see. So 2, 3, not 4, 5. So there's 3 ways, 3/6. So so half the time you expect to get a prime number when you roll a dice. Okay, what about the odd part? Okay, so now we're going to add that. We're going to add that probability together. So that's out of 6. How many ways can you get an odd? 1, 2, 3, 4, 5. There's 3 ways to get a prime. So 3. So 3/6. Well, if I add 3/6 and 3/6 together, I get 6/6, which is 1. Oh, that means that, and remember, this is the wrong way to do it. That means that I should get a prime or an odd every single time that I roll the dice. Well, that's not going to happen, because what if you roll a 4? So something's wrong with our reasoning here. What happened? Well, this is a simple enough problem that we can fall back on our basic definitional way of calculating probability to see what's going on here. So let's do it that way. We'll just calculate it directly. So out of a sample size of 6, we're going to count both. So let's see. 1 is an odd. It's not a prime. 2 is a prime. 3 is a prime. 4 is not a prime, and it's not odd. 5 is odd. And 6 is not prime, and it is not odd. Okay, so that's only 4. So that's 4 out of 6 times equal to 2 out of 3, right? 2/3. So let's see. Let's make sense of this. When we do the intuitive version, which is where people want to add together the 2 probabilities, we got that you should expect to get an odd or a prime every single time. But when I just went back and we relied on the basic fundamentals, we got that you should get a prime or an odd 2 out of 3 times. So what's the difference? And the answer is the numbers 5 and 3. Notice that up here, when we calculated the primes, 3 and 5 were counted in this probability, right? But 3 and 5 are also odd, so they were counted in this probability. So actually, the probabilities involving the numbers 3 and 5 ended up in this first fraction and the second fraction. In other words, we double counted those numbers. So if you just take 2 probabilities and add them together, there's a decent chance that at least at some time you will be double counting your probabilities, and your probability will come in higher than it actually is. That's what this piece in the formula is. This, where was it? This minus the probability of A and B, that's subtracting back off your double counting. Because right here, when we did P of A plus P of B, 3 and 5 got counted in both. So the probability of A and B, which would be an odd and a prime, that's the probability of getting a 3 or a 5, so we subtract that off. So you double count it here, and then you subtract off part of your double count so that you get the actual probability. That's what's going on. So, I can't tell you how many times people just treat this as, anytime they have to do the addition rule, it's just P of A plus P of B. And then they don't understand, why did I get a probability that's wrong? Why did I get a probability greater than 1? None of this makes sense. It's because they didn't subtract off the double count. That's what we would do up here. If we wanted to change this to the correct way, we would go 3/6 plus 3/6. How many ways can we get a prime that is odd? 2 ways. So then we would subtract off 2/6, And notice that now it works. Now our answer is correct. This is correct as well now. Notice how they match? Because we did it correctly. We got 4/6 for both of them because we used the formula correctly up here. So you add together the probabilities and you subtract off the number of the probability of both events occurring. Okay, so you get rid of that double count. Here we had the problem was simple enough that we had the benefit of being able to calculate the problem two ways. A lot of times you're not going to have that. You're going to have to rely on the formula, which means you're going to have to know how to use it correctly. Okay. Okay, so here's an important definition for us. Let me move this over just slightly. Events A and B are disjoint, or sometimes you might hear people use the term mutually exclusive. In mathematics, we tend to just use the term disjoint if they cannot occur at the same time, right? So two things cannot occur. So this would be some disjoint events. Let's say I roll a dice. I can roll an even number or I can roll an odd number, but I can't roll a number that is both even and odd. Those are disjoint. They are mutually exclusive. If you have one, you don't have the other. Our example we just looked at a moment ago, odds and prime, those are not mutually exclusive, right? Because the number 3 is both odd and prime. The number 5 is odd and prime. So primes and odd are not mutually exclusive, right? Think about flipping a coin. If you flip a coin, can you get heads and tails on the same flip? No, those are mutually exclusive. If you get heads, you didn't get tails, right? So, and here's some example, randomly selecting someone who is a registered Democrat, randomly selecting someone who is a registered Republican. Generally with the state, when you register as one party, either Democrat, Republican, Independent. It varies from state to state how you can register for stuff. But if you're a registered Democrat, then you're not you are not registered Republican, and vice versa, right? Here they give some examples of events that are not disjoint. Randomly selecting someone taking a statistics course, randomly selecting someone who is female. Those aren't disjoint because, as we know, there are females in the class, and so you can be both female and a student in a statistics course. Those are not mutually exclusive. They are not disjoint. Okay. So some of you may have seen Venn diagrams before. A Venn diagram is just a way of picturing how your sets relate. So this means that this is the Venn diagram for things that are not disjoint, right? So maybe blue is people in statistics class and yellow is females. And of course, we know that there is overlap. There are female statistics students, so that would fall right here where you're in both of them. Okay, this is the example. This would be like for numbers. You've got odds over here, evens over here. There's no number that is even and odd. They are separate from each other. Okay, so just always think about that whenever you're about to add probabilities together. Stop and go, wait a minute. Are there things that are both of these? Because if so, then you have to be much more careful with your counting, right? If two things are disjoint, then we can just get away with adding the probabilities, right? The probability of rolling a dice and getting a 4 or a 5, those events are disjoint. You can't get a 4 and a 5 on the same roll of one dice. So in that case, since they're disjoint, there's no double counting going on, meaning we can just add those probabilities together. 1/6 plus 1/6 will be 2/6, which is 1/3, right? No double count. But as soon as you start talking about things that overlap, so just always ask yourself, can we have a female who is also a statistics student? Yes. Okay, then you have to use this formal formula right here for your probability. Can we have an odd that is also a prime? Yes. Then you have to use this minus p of a and b piece in order for it to make sense. Okay. Yeah, and they even say here, errors made applying the addition rule often involve double counting. That is, events that are not disjoint are treated as if they were. I can tell you almost probably almost all of you will do this at least once in the homework, and then hopefully most of you go, oh, that's what he was talking about in class, and then you'll fix it, and then you'll not make that mistake again, right? But some people keep making that mistake again and again and again. You know for sure that you did it wrong if your probability comes in greater than 1, because the probability can't be bigger than 1. But like in the dice problem we did, we got it wrong, and that number was not bigger than 1, right? It added up to 1. So depending on your problem, it's not always obvious that you added up your probabilities incorrectly. Okay, complementary events. This is more helpful than students think it is at first in general. I think there's a tendency to dismiss this argument on complements, but there are problems in the homework that you're going to find will be easier if you understand this complementary event rule, right? I was just helping a student yesterday during office hours with one of the homework problems, and she was like, there was like a probability question. This is for my other class, because they're sort of finishing up probability. She was doing a problem from the homework that had like 5 parts. There was like parts A, B, C, D, and E. And they were slowly building and getting more complicated. And like parts A and B were pretty easy. C took a little bit more work. And then she got to this one part D, and she's like, I can't figure out the probabilities because this is like so complicated. I can't figure out how to count the pieces that I need to count for the numerator and the denominator for the probability. And you weren't supposed to do that because it would be like some of these problems, like I say, very, very complicated to calculate the probabilities directly from the definition. But what she was supposed to recognize in that problem was that part D was the complement of part C. So since she had already calculated part C, if you recognize the complement, then D is like super easy. If you don't and you try to calculate the probability directly, it's like brutally hard. Like it would take forever, and sometimes they're not even doable, right? So here's what you do. Complementary events are things that are the opposite. So if you can take something and just divide it into 2 outcomes, like 2 groups of outcomes that take up the whole sample space, that's complementary. So rolling a dice, and you would have, if A is rolling an even, then the complement would be rolling an odd, right? Because the evens and odds take up all possibilities, and there's no overlap. They are disjoint, right? So if I roll the dice, it's either an even or an odd. Those are complementary events. A complementary event sometimes would be also, for instance, let's say I roll 6 dice and I don't get any 6s. So maybe you're playing Yahtzee, right? You roll 5 dice. Do people still know what Yahtzee is? It's a game where you roll dice and then you try to score certain values. Probably no one's ever seen Yahtzee anymore. But you roll 5 dice, you look at the numbers on the dice, and then you make decisions about how you want to score certain things. So you can roll 5 dice and not get any 6s, right? So what's the complement of the event where I roll 5 dices and I don't get any 6s? And a lot of times people will say the complement would be where you roll the dice and you get all 6s. No, that's not the complement, because there's other possibilities that don't fit into those 2 categories, right? So the probability, or the event of rolling 5 dice and not getting any 6s is that you roll the dice and you get at least 1 6. So you're going to start seeing that in the homework. When you see things like at least 1, start thinking, maybe I should use the complement. Because if you want to calculate the probability of rolling dice and getting at least 1 6, it's going to take some work, because you have to calculate the probability of getting 1 6, plus the probability of getting 2 6s, plus 3 6s, plus 4 6s, plus 5 6s. And then you have to adjust for, depending on how you counted, any double counting that occurred. Okay, that's going to take a lot of work. Or what you can recognize is, well, there's the probability of not getting any 6s, which is pretty easy to calculate. That's going to be 5 6 times 5 6 times 5 6 times 5, 5 times. The complement is just 1 minus that. So you can remember this rule pretty easily. For complementary events, the probability has to add up to 1. So the probability of getting if I roll 1 dice, the probability of getting an even plus the probability of getting an odd equals 1, because that's the whole space. So this first formula hopefully makes a lot of sense. Once we have that, we can easily manipulate this using algebra, your tools from algebra, and just subtract something around. Like these look complicated to people. These are the same as just an x and a y. So what did we do before? We would like subtract x from both sides. Now you're subtracting p of a from both sides. So the probability of the complement is 1 minus the probability of the event. So the probability of getting at least 1 6 when I roll 5 dice will be 1 minus the probability of getting no 6s, right? So if you already calculated the probability of getting no 6s in part C, then in part D, it's very easy. You just do 1 minus the what you got in part C. But if you try to calculate part C directly, you're going to be in for some work. Doable, but you're in for some work, okay? So let's look at an example here, right? And this one's kind of overly simple, but the probability, okay, well, actually, I don't love this example. Let's look at it this way. Let's say the probability, you're going to roll 1 dice. What's the probability that you roll 1 dice and you get a 2 or a 3? Well, it's going to be 2 out of 6 or 1/3, right? So what's the probability that you don't roll a 2 or 3? Well, that would be that you roll a 1, a 4, a 5, or a 6. That's 4/6 or 2/3. And you can see if we add 1/3 to 2/3, we get 1. Those add up to 1 together. So can be helpful. I know a lot of times students, it's just that they don't recognize the events they're dealing with are complementary because you haven't dealt with this enough. You'll start to recognize language where you read a certain problem and you go, oh, is that a complement type problem? I think it might be. And then you can, answer it accordingly. Okay, let's go here. Feel free to ask questions if you have any. Okay, so we just talked about what happens when you have or. So whenever you have an or statement, you should think of addition. I'm going to be adding probabilities together, except there's that one important piece. You subtract off any double counting that occurred. If you do that, you're good to go with that. So that was for or. When you hear someone say, what's the probability that I roll a 2 or a 3? I think a lot of people don't understand how important the words and or are in mathematics. The entire foundation of mathematics relies on the words and or. The basic logic that is used to construct mathematics uses those words and or. Okay, so, a lot of times people that maybe don't, they're just maybe not strong readers or something, so they're not real critical when they're reading. They're not really good at like dissecting what they're reading and pulling apart the meaning from paragraphs. A lot of times people will miss those ands and ors and just kind of think, well, there's two things we're talking about, right? But it matters. Are we talking about an and or an or situation, right? Right. So here's our basic notation. So the probability of A and B, right? So the probability that both of these events occur. Before it was one event occurs or the other event or both. In mathematics, we use what's called the inclusive or. You may have learned about this in an English class. You can ask your teacher. There's 2 types of ors that we use. And you're like, what are you talking about? I use the word or all the time. There's just one. No, there's inclusive or and exclusive or. And you probably use both without even really thinking about the fact that you're using both, because usually what happens is we draw from context. Are we talking about the inclusive or the exclusive or? So if your friend says, hey, it's your birthday today, do you want me to take you out to lunch or do you want me to take you out to dinner? You're probably not going to go, yeah, both. Why don't you do both of those for me? I'd really appreciate you giving me a lunch and a dinner. That would be cool. That'd kind of be considered rude, right? Kind of being greedy with your friend's generosity, trying to make your birthday nice. It's understood when your friend asks, do you want me to take you out to lunch or do you want me to take you out to dinner? They mean the exclusive or, which means the lunch or the dinner, but it's kind of implied not both, right? That would be kind of rude. So in that case, you draw context from the problem. Oh, we're talking about the exclusive or. In mathematics, unless we specifically state so, we are always using the inclusive or. So like some of you who go into computer science, you'll see there's this thing in there called XOR. That's exclusive or, right? That's where they are specifically stating we are using the exclusive or for this problem that we're solving right now. Because otherwise mathematics assumes the inclusive or, which means both. That would mean you could say, oh, you said or, so that means I can have both too. So yeah, I'll take lunch and dinner, right? Sort of the humanity comes in, and we don't do that to our friends when they offer. So you just want to always ask yourself, am I dealing with an inclusive or an exclusive or? Usually in mathematics, we're dealing with the inclusive or. So then we have our and. And means both. The probability of A and B occurring. It's the probability that event A occurs in the first trial and event B occurs in the second trial. So, and you can move that language around a little bit, but basically you have two things happening, two conditions that have to be satisfied. Okay. Right. Then we have the probability of B given A. This is how you read this with this line. The probability of B given A. So the probability of B given that A has already occurred, right? So you could say, what's the probability? We'll do an example down here. Coming up, a couple more things we want to come up with first. So here's our let's do this definition. Two events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other. So sometimes people confuse disjoint and independent. Those are different. Disjoint meant that the events can't occur at the same time. Independent means that the probability does not affect the other one. So for instance, we talked about this earlier. You're going to play roulette, right? That little ball going around doesn't remember the previous outcomes. So the fact that it landed on red doesn't affect the next roll at all. It doesn't make it more likely that it's going to come up black the next time on the next roll. When you flip a coin, if it comes up tails 15 times in a row, that next flip is still independent. That next flip is not affected by the last 15 flips that you did, right? There's nothing in the universe that's making it balance out and say, well, you did just have 15 tails in a row. The next one better come up heads. Like the coin doesn't remember, okay? So those events would be independent. The probability of one does not affect the probability of the other. And do not think that, here's a caution they throw, do not think that the dependence of two events means that one is direct cause of the other, right? So for example, having a working TV in your room and having working lights in your room are dependent events, because if they cut the power to your room, you lose both. But the TV is not causing your lights and the lights are not causing your TV, but they depend on something else. It's almost like that idea of a lurking variable we talked about earlier in the semester, where there is something that is affecting both of these. So they are dependent on each other in some way, although it is possible to have the TV on and not the lights, and the lights on and not the TV. If the breaker for your room blows, then they both go out together. In that way, they are at least partially dependent on each other. All right, and then there's another idea that we really need to get comfortable with, and that's with replacement or without replacement. Okay, so when you do with replacement, selections are independent events. Without replacement, selections are dependent events. So here's an example. Let's say we were all sitting in a classroom, and I had a deck of cards. And I said, whoever gets the ace of spades from this deck, whoever pulls the ace of spades from this deck, you get an A on your project. You don't even have to do the project. You just get an A. You get an A in the class, and you can just go home now and not do anything else, right? Obviously, I'm not going to do that. But let's just say that was the game we were playing. Okay, I've got a deck of cards. I'm going to go to each person in the room, and whoever pulls that ace of spades, you get an A, and you're out of here. Go home and go get some tacos or whatever, and and then enjoy that you don't have to do any more statistics homework, right? You don't have to stick around. Everyone else is going to have to stick around and work. So I'm going around the room. I've got my deck of cards. Whether I do that with replacement or without replacement will make a difference in the probabilities of you pulling that ace of spades. So, for example, I go to the first person. All right, there's 52 cards in a deck. There's one ace of spades. So the probability of that person pulling the ace of spades is 1 out of 52. Okay, so probably not going to happen, right? Unlikely. Could happen, but pretty low. Okay, now the question is, do I let that first person keep the card that they pulled, or do I make them put it back in the deck? So think about it this way. They pull their person number 1. They pull that card, and they put it back in the deck. They look at it and go, oh, not the ace of spades, and maybe it's the 10 of hearts. They put it back in the deck. I go to person number 2. Okay, that deck is still intact, right? Because we put the card back in, so it's still 52 cards. That next person, their likelihood of pulling the ace of spades is 1 out of 52. They pull the card. No, wrong card. Put it back in the deck. I go to the next person. We could go through the entire class like that. The probability of every individual in there would be 1 out of 52, because the fact that the previous people did not pull the ace of spades out of the deck doesn't affect whether you pull the ace of spades out of the deck, right? Nothing's changed about that problem. Those are independent events. We call that with replacement, which basically means after each trial, we reset what we're doing. The deck is getting reset because the card that someone pulled, they're putting back in. Okay, so if you're like the number 3 person, you have the same probability as the number 1 person because the problem is being reset each time. Now imagine this way of doing it. I go to the person number 1 and say, okay, we all know the rules. If you pull the ace of spades, you get an A in the class. So person number 1 pulls the card. It's not the ace of spades. It's the 10 of hearts. They put it down on the table. They do not put it back in the deck. And I go to person number 2. Now, person number 1 had a 1 out of 52 probability of getting the ace of spades. What is the probability for person number 2? Well, there is one ace of spades card left, but now there's only 51 cards left in my hand, right? Because person number 1 kept the card. So now person number 2 has a little bit better probability. Person number 1 had a 1 out of 52 probability. Person number 2 has a 1 out of 51 probability. Still low probability, somewhere around 2%, but better than the first person. So they pull a card, they look at it, it's the 7 of clubs, darn, wrong one. They stick it on the table. They do not put it back in the deck. So I go to the third person. They have a 1 out of 50 chance of pulling the ace of spades, because see how we have one less card in the deck each time? So actually the probabilities are getting better. So in this kind of situation, you'd kind of want to be in the back half of the room a little bit, or maybe in the middle of the room in order to increase your chances. If you're up front, you're some of the first people I go to and give a card, your probabilities are lower. But once 30 cards have been pulled from the deck, right, I go to the middle of the room, 30 people have pulled cards. That next person has a 1 out of 22. That's a much better probability. Would you rather have a 1 out of 22 probability of getting an A or a 1 out of 52 probability? You'd rather have the 1 out of 22, right? So in this case, we are doing without replacement because we're not replacing the card back in the deck, and yet those events are dependent because if you're in the middle, you pulling that card depends on everyone that came before you. If someone pulled the ace of spades before you, then it's game over, right? But your probability is dependent on theirs because each time someone pulls a card and fails, your probability gets a little bit better. Okay, so that's how we do with replacement versus without replacement. The calculations are different, and you should always ask yourself, there's like a series of questions. Every time you do a probability problem, ask yourself, let's see, are these events disjoint? Okay. Are they independent or dependent? Is this with replacement, without replacement? Is that appropriate for this problem? You ask yourself that series of questions, and then you're able to figure out how to calculate the probability that you're trying to calculate. Okay. We'll get into some stuff there. Right, so we just kind of did an example. Okay, and here's one. With probability, you really have to be careful with language. It's very easy to do probabilities incorrectly because it kind of goes back to what I was talking about a few minutes ago, that critical reading, right? If your reading skills are weak, probability can be very difficult because what you'll actually end up doing is calculating a different probability than the one you were intended to. So I see this all the time, these misinterpretations of what you're doing. So listen to the following sentences. Imagine we're all in a classroom together, okay? Find the probability that two people are born on the same day of the week versus find the probability that the two people are born on Monday. So we're in our classroom. We randomly pick two people from the classroom, and we have two questions. The probability that the two people were born on the same day of the week versus the probability that the two people were born on a Monday. And then someone will raise their hand and say, those are the same thing. And I'll go, are you sure? And they'll say, yeah, because if you were both born on Monday, then you were both born on the same day of the week. Okay, so that's sort of the implication one direction. What about the other direction? If two people are born on the same day of the week, does that mean that they were both born on a Monday? No, it doesn't work that direction, right? So you have to be able to read critically and break down the differences between these types of problems because you come up with a very different calculation. So how would we do this? Well, we pick two people in the room. Person number one was born on a day of the week, right? What day of the week were you born? I was born on a Saturday. Okay, so person number one was born on a Saturday. Now we go and pick person number two. What is the probability that person number two was born on a Saturday? Well, it's 1/7, right? 1 out of 7. So the probability of picking two people in the room and that they were born on the same day of the week is 1 out of 7, 1/7. Okay? Now, what's the probability that we randomly picked two people and they were both born on Monday? You would expect that probability to be lower because it is a more restrictive restraint, right? So I pick person number one. What's the probability they were born on a Monday? 1/7, right? 1 out of 7 days. Okay. Now we go to person number two. What's the probability they were born on a Monday? 1/7. So this is where we use that multiplication rule. 1/7 times 1/7 is 1/49. So you can see one of these probabilities is like 7 times the other one. It's 7 times more likely that two people were born on the same day of the week than that they were both born on a Monday. But some people will do this problem the exact same way. And look, when I first learned probability, it confused me. I had trouble with it. And part of that is because, and even now, sometimes I'll start working on a probability problem and I'll work on it a little bit and go, oh, I'm interpreting this problem wrong. And then I have to start over and go, oh, I see how to do this problem, right? So probability is not intrinsically easy. Like your basic definitional problems are. But when you start getting into things complicated like this, it takes a little practice to get good at. So don't be too hard on yourself. Don't go, I can't do probability. You can, but it takes, it's like anything in life. It takes some working on it to get good at it. Like your painting, first painting you ever make is going to be awful, right? But if you keep working at painting, it's going to look good. And then people are going to go, wow, you're amazing. You do all this painting. And they don't recognize that well, yeah, this is like my 100th painting that I've done. Right? They sort of dismiss all that work. So read carefully when you're doing the problems. Let's see. What do we got? A couple minutes. Let's see. I can talk about that example. Yeah, okay. Let's talk about this one for a couple minutes. So we've got modern aircraft have a bunch of redundancy in them because if they didn't, then whenever something went wrong on an airplane, it would crash and then people would die. So what they do in an airplane is they have redundant systems that are separate. They're independent of each other, right? Like totally separate systems. So like in this example, the hydraulic system, right? The probability of a hydraulic system failure is 0.002. That seems low, but it's not that low. Right, that is 1/5 of 1%. So that means out of every 1,000 flights, one would crash. Right, if I'm doing that right in my head, that's not very good because there's like tens of thousands of flights a day. That would mean we'd have multiple plane crashes, like a dozen plane crashes every day. That's not good. So hydraulic system failure of 0.002 isn't good enough. I'm not getting on a plane where every 1,000 times it flies, it's going to crash. Right. So what they do is they put in 3 independent systems, right? They're not even connected. That way, if one goes bad, it doesn't affect the other ones. So then your system is, you increase the likelihood of surviving a plane flight significantly because if one of your hydraulic system fails, because that's 1 out of 1,000, the other 2 are still working. Right? So then you might want to go, well, now what's the probability that all 3 fail? What is that probability? So let's get into these questions here. If the Airbus 310 were to have one hydraulic system, what is the probability that it would work in a flight? Well, here's our complement. If the probability of failure is 0.002, then remember, according to our formula, 1 minus the probability of failure would be the probability that it doesn't fail. So that's 0.998. So 99.8% of the time, it's going to work properly, which isn't great. Okay, what if we have the 3 independent hydraulic systems? Flight control will be maintained provided one of the 3 systems does not fail, right? So we really want to know what's the probability that at least one of these keeps working, right? Remember that at least one, that should be a red flag you're probably going to use. You're probably going to use the complement. So it follows that the probability of maintaining flight controls as follows. The probability that it does not happen that all 3 hydraulic systems fail. That means at least one is still working. So 1 minus 0.000008. Where did this number come from? That's 0.002 times 0.002 times 0.002, which is the probability of each system failing. So now it's really low. Now we have a really high probability, right? That's much better. Would you rather get on a flight that had a 99.8% chance of getting you to your destination alive? Or would you rather get on a plane that had a 99.9999992 probability of getting you where you needed to go? I'm getting on the second flight. I'm getting on this one, right? So that's how you work through those problems. And we are out of time. That's your addition and multiplication rule. So just practice them. People are usually good with the multiplication rule. It's the addition one that messes them up because they forget to cancel off the double count. That's the one that messes people up. Okay? So be aware of your due dates. Keep track of all that kind of stuff. And let's see, what is today, Wednesday? Excuse me, I keep getting hiccups. And I'll see you next week, okay? So, and there's office hours tomorrow. Otherwise, I'll see you later. Okay, thanks. Anyone who wants to talk to me in Zoom, hop over and do it.